Okay, so we're starting here and we're trying to determine what kind of compound we're looking at. This is where you're given a chemical formula or you know what elements are involved in the chemical bond. So the first question that I ask, the little mental checklist that I go through is there a metal? And if there is a metal, then the next question I'm looking at is it only metals or is there a non-metal? And if the answer is no, if it's only metals, then you're looking at a metallic bond. And we're saying this is a pure metal. And then we talked about metallic bonds last time where we have this sea of electron sharing where the metals conduct electricity really well. And it's called a sea of electrons because the electrons are easily shared amongst the series of metals in the solid or liquid form. If there is a non-metal as well, then we get into an ionic bond. And there's a couple specifics of the ionic bond that, as far as naming goes, as far as how do we name them and what type of ionic do we have, that I want to get into as well. And if there's an ionic bond, if there's just, the next question is, are there only two atoms or are there more than two? Or two elements? Or three or more? Because based on how many elements are involved in the ionic compound, it's going to determine how we name the compound or what particles are involved in the compound. So when it's only two elements, it's called a binary ionic. And we had the cation, the anion, and we used an IDE ending. At the end, we changed the anion to have an IDE ending, and that was the chemical name. The formula is still, you're trying to balance the charges. You're using the charges to determine the ratio of the elements in the compound. We did that with the ion bubbles that we were moving around and balancing charges with. But most of the ones we worked with were binary ionics, where there's just two elements, one's a metal and one's a non-metal. So if there are three or more elements, and I'll give some examples of what compounds look like for each of these. If there's three or more elements involved in the ionic bond, then it has a polyatomic in there. It has polyatomics, which means that they have names. You're going to check your common ion list, but you're not going to necessarily give it an IDE ending, is because the polyatomics, whether it's the cation or the anion, they have special names. So it's still the cation plus anion, but instead you're going to use the name given on the common ion list. And you're not going to have an IDE ending. There's a couple that do have them, but you're going to check because the anion especially could have 8, ite, ide. There's a lot of possibilities. It could be 8, ite, it could be ide. There's a lot of possibilities based on the structure of the compound. You don't have to get into too much of memorization on whether it's 8 or ite, how many oxygens for 8, how many oxygens for ite. You do have the common ion list that you can reference, but I'll also give you the structure if I need you to balance the charges. I'll give you the structure with the charge, and then you just have to make sure to write the formula correct. So I'll help you out a little bit if it's a matter of between 8 and ite or any of those details. So we have metallic bonds and we have the ionic bonds. I'm going to do some examples in some green writing. So metallic bonds, some examples would be just a chemical, as far as chemical formulas are concerned, what you would look like or would you look at is just Fe for iron, or maybe bronze is an alloy. We can have a sheet of silver, pure silver, and you either just write the element, the metal by itself, or some name of the alloy. And then for binary ionics, We had calcium chloride. A lot of the ones from assignment 4, assignment 2, 1 and 2 are binary ionics. Calcium chloride, sodium nitride is the name of a binary ionic where I've changed the nitrogen to nitride. Those would be examples of the binary ionic, just 2 elements. Now for the polyatomics, if I have something like calcium but with carbonate, then you have the name of the cation calcium, and the CO3 is called carbonate. And so that name encompasses carbon with 3 oxygen, is lumped into that name, carbonate. You could have iron nitrate, and this is where we saw parentheses to show how many nitrates there are. This would be 1 iron, this would be iron 2, or Fe plus 2, and this would have 2 nitrate ions as well. The nitrate is the NO3 minus 1 ion, but because we're balancing charges, we see that we need parentheses if we have more than 1. So if there's a metal, is it, actually from here would be better, for the ionic bond, is the metal a transition metal? And if it is, then we need to use Roman numerals to identify the charge. So if there is a metal somewhere in the compound, it's either metallic or ionic. And then we'll go ahead and clear all this and re-ask the question, is there a metal? And if the answer is no, let's talk about covalent compounds. Spelled correctly at some point, covalent compound. So the covalent compound is only nonmetals. And when you have only nonmetals, they're not ionizing. You're not ionizing, you're just sharing electrons. And the goal is to achieve an octet. So covalent compounds are sharing electrons. So all atoms have an octet, which is 8. And we had some exceptions that we wrote down last time, but I'll write the exceptions here. The exceptions here is hydrogen is okay with 2, beryllium is okay with just 4, and boron is okay with 6. But everything else we're working with right now is gonna max out at 8, and that's their goal. That's a predictable end point that we're gonna try and reach with our structures. And we're gonna represent valence electrons bonding or what the valence electrons are doing using Lewis structures. Which we're going to be getting into more today. Covalent compounds can be modeled with Lewis structures, and we'll get into the criteria that today. That's going to be the bulk of today's, looking at some more Lewis structures and some possibilities with that. But as far as naming goes, we're only going to be dealing with binaries as far as the names go. A binary molecule. So we use the term molecule specifically for covalent compounds because when we draw these structures, there's a starting point and an end point. The molecule is contained. There's only a couple of atoms to it, and the structure represents the entire molecule. Whereas for ionic, we're showing a ratio in which they bond, but ionic compounds it's a repeating pattern. Ionics and metallics just are repeating patterns over and over and over again, and we're just representing a small portion of that with our formula. Whereas the covalent compound, the chemical formula is the molecule, and that's it. That's the stop point. And yes, those molecules we can have a source of a ton of those molecules all near each other, but each molecule is not connecting to each other through a bond the way that ionics and metallics are. Each molecule is contained, and that's it. And then we have a source of all different types of those molecules. So we're going to be able to name these binary ionics. And I want to expand upon the naming schemes. And so the big thing about this one is we're going to use prefixes, which we haven't seen yet. We're going to use prefixes to show how many of each element is in the chemical bond as far as to name them. So for the chemical name, we're going to use prefixes. And that's what I want to show you next. So when we are working with covalent compounds, it's nonmetals only. So the nonmetals are going to be hydrogen. And then we have boron. Silicon can covalently bond. Actually, let me loop all these in here. So boron, pretty much any of these to the right of the zigzag line. And then as far as the noble gases, we're not going to bond with noble gases right now because the noble gases are considered inert. They're not going to chemically bond. So group 18 is chemically inert, doesn't bond. Now, technically, there are types of chemical bonds that can form with krypton and xenon, but for our purposes, we're not going to be looking at those. So these are the nonmetals. These are the nonmetals, and when you are dealing with covalent compounds, essentially you just choose two of these elements and put them together and say, okay, what kind of bonds form? And there's a lot of variety. I want to show you an example of why we have our naming rules with prefixes, because when you pit two elements together, there's a variety of combinations that they can make. So these are the nonmetals. The rest of them are metals. The rest of these things are metals, but what I've highlighted are nonmetals only. And one of the most important ones is carbon. We're made of carbon. Carbon has a great variety. Carbon, I did this last time, carbon, nitrogen, oxygen, phosphorus, sulfur, and hydrogen. Those are the 6 most important elements when you're talking about life and us. So, naming binary ionics. Oh, excuse me, covalents. So here's how this is going to work. We have two names, or two words. First word, second word. The second element still has that IDE ending. And when you hear some of the compounds, these are ones that you've heard before. Covalent compounds are more common compounds that you've heard just in casual speak throughout your life so far. So what we need to focus on is the prefix. So we have a prefix and a prefix. So we're going to use prefixes to help us describe how many of that element exists in the chemical formula. So I need to give you these prefixes. I need to tell you what they are. So if there's a value of 1, the prefix is mono. Now, the unique thing about mono is I'll get back to it. So mono is 1, 2 is di, 3 is tri, 4 is tetra. Fun little story about tetra is that's where Tetris came from. And the idea behind Tetris is every single block is made out of 4 smaller blocks. And if you get a line of 4, it's called getting a Tetris. So I don't know if Tetris has made a resurgence lately, but 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. And I skipped a little bit for mono because mono is only used on the second element. If the first element only has 1, you're not going to put mono in front of it. You only use mono if it's the second element that has 1. And I'll give you some examples, and you're going to start making connections to words you've heard before and these rules that we're seeing today. So the first two you've heard of. We're not going to use mono on the first one because if there's just 1, you do not use mono on first element. So we're just going to say carbon. But the second oxygen only has 1, so we're going to say carbon monoxide. So we have the prefix and we have the IDE ending on the second word. And then the second one is carbon, but this time it's dioxide. Whereas if we use the original ionic names, if we just name this like an ionic compound, we just say carbon oxide, and there would be no way to differentiate between them. But now with covalent compounds, we have to have a way to differentiate between how many oxygens are in this compound. Practice using prefixes, writing out the name for C2O4, and then P3F7. What do you think that would look like? Try that out right now. I'll pause for a moment. So the 2 is dicarbon, and the 4 is tetra. And then now if we have tetraoxide, this A and U next to each other, we can actually combine that and just say tetroxide. So you drop the A if you have oxide. Now I'm not going to be checking your spelling in a test this week, but that's just something that happens, so don't freak out when that happens. So we have a 3 and a 7 we need to use prefixes for. So we have tri, and then phos, for us, I'm taking some liberties, I'm using some space, so triphosphorus, and then hepta. Then this next one I have to change to an IDE ending, so fluorine will be fluoride. That's it. That's how you name covalent compounds, at least the binary ones that we're working on right now. Here's the big question. When do you know a Lewis structure is correct? And this is the approach that we're going to take for more complicated structures, ones that you're not drawing from scratch, but rather you're choosing from a list of given structures, and you have to choose the one that's correct. And these are the type of questions that are going to be showing up a little bit more on the assessment. For a free response question, I may ask you to draw one from scratch, but these are going to be basic ones like draw the water molecule or draw NH3. And these are ones we've seen over and over and over again. And on your, if you have your homework done, it will be one similar to ones that you've already done on your homework. But let's go through and look at some more complicated structures and ask the question, how do we know when this is correct? And there's two main things that you need to check right now. Two main things. First thing, are all of the valence electrons exactly the number of total electrons? Is the total number of valence electrons correct? Correctly shown. Meaning we're going to have a way of counting valence electrons in a model, and we're going to check to see if the model is actually using the correct number of valence electrons. For example, if I have a compound like CO2, and I want to just know how many total electrons should I be drawing, how many valence electrons are involved here. Well, each carbon has 4 valence electrons. Each oxygen has 6 valence electrons. But because we have 2 oxygens, we're going to multiply that 6 by 2. And we're just going to get a total. So carbon dioxide should have 6 times 2 is 12, plus another 4 is 16. So whatever structure we draw for carbon dioxide better show exactly 16 electrons, whether it's through those lines, bonded electrons, or the extra dots, the non-bonding electrons. So a correct Lewis structure for carbon dioxide would be carbon in the middle, double bonded to each carbon, and some extra dots around the oxygen. So when I look at this structure, I should be able to count all of the electrons shown and get exactly 16. So the way I do that, and it's kind of hard to show you digitally, but I'm going to do the 2, 4, 6, 8 counting, and I'll show you how I'm adding that up. So these two, right, these are 2, and this next set is another 2 to get me 4, so I'm counting 2, 4, then 6, 8, 10, 12, 14, and then this last pair would get me up to 16. So once I get up to 16, I count up to 16. I know that I've drawn all of the valence electrons that I need to, exactly 16, no more, no less. Check for octets. And this is going to be the magic number, 8. So if we look at carbon dioxide, again, where are the octets? And so what I'm going to do is draw some circles to show locally what I'm looking at. I'll give you a moment to get this drawn again. So this is the bigger indicator. This is the one that I'm constantly looking at. Just focusing on oxygen, these are the electrons immediately touching oxygen. And so we have 2, 4, 6, 8. There's just sets of 2, 2, 4, 6, 8. So that one on the left has 8 oxygens, And the oxygen on the right is the mirror image, essentially. So both of those oxygens have octets. And then this carbon in the center has a total of 4 lines coming off of it. Each line represents 2 electrons. So 2, 4, 6, 8. And so this is how oxygen gets its octet as well, by having 2 double bonds, essentially. So if I combine them all together, this is kind of the field of view I'm looking at from each atom. And you notice the bonds are overlapping space between the elements. So this double bond counts for both oxygen and carbon, and the other double bond counts for both oxygen and carbon. And this is my counting that I'm doing. So everything has an octet. All elements in this case have an octet. Now the exceptions are, of course, what I wrote on the previous page. Hydrogen only needs 2, which is a single bond. Beryllium gets 4, and boron only needs 6. For example, if you had boron only has 3 valence electrons. So a very common compound for boron is making just by doing the connect the dot method, is 3 single bonds to 3 different hydrogens. This would be boron trihydride, to use the naming scheme we just practiced. And so that's one way that boron is stable. This is not an octet, it's only 6, but for boron, that's okay. But anything after boron, carbon, nitrogen, oxygen, phosphorus, sulfur, fluorine, all the other nonmetals are going to need 8 for right now, for our purposes. Now, again, technically, there's ways that some of these atoms can have more than 8, 10, 12, 14, 16. And those are larger structures, more complicated structures. We don't get into that right now. So right now, the magic number is 8. So I'm going to show us some compounds. I'm going to show some drawings, and we're going to determine which ones are correct and which ones are incorrect. So this is our first set for carbon monoxide. Which structure do you feel is the most correct? And so you're looking for those 2 things. How many total electrons, total valence electrons, and octets. If the structure satisfies both of those, it should be the correct structure, and only one of these is correct. So take a moment to try this out and type a letter in chat which you feel the correct structure is. And I'm going to go ahead and set up another one so we have 2 examples. So here's our second example as well. Choose the correct structure. So we need to figure out the total number of electrons available. Carbon brings 4 valence electrons. Oxygen brings 6 valence electrons. And since there's 1 carbon, 1 oxygen, we're looking for 10 electrons shown. Only 10. And for N2O, there's 2 nitrogens, so those are each 5. And again, oxygen is 6, so this should be 16 electrons for the second one. Let's go through the first one. What I'm going to do is first just count total number of electrons. And so the way I'm counting is going 2, oops, that is the eraser. Never mind. 2, 4, 6, 8, 10, 12, 14. If I'm just counting each of those pairs, this one gets up to 14. A has 14, so that is not a correct structure. Already, I can cancel that one out. For B, it goes 2, 4, 6, 8, 10. Okay, so it does have 10 electrons, which is what I'm looking for. And let's check the last one. 2, 4, 6, 8, 10. Each of those lines count for 2. So this one also has the correct number of electrons. So far, B or C are possibilities. So now we need to go back and check to see if they have an octet. So I'm going to go ahead and erase my blue marks because I know they have 10. And let's go check for, I'll leave that one up just because, there we go. So now let's check for octets. What I'm going to do is I'm going to circle this carbon, These are the electrons that carbon has access to that are immediately touching carbon. And here, already this carbon only has 6. 2, 4, 6. The double bond and the 2 extra dots. So this is not an octet. So B is incorrect. A is incorrect, B is incorrect. So let's just double check choice C to see that C is correct. If I look at the carbon here, that's an octet. 6 from the triple bond and an extra 2 are on carbon. And if I go from oxygen's perspective, these are the electrons oxygen has access to, and that's also an octet. So both of them have an octet. So C is the correct structure for number 1. Let's start by checking octets. We'll flip it and check for octets. So that is an octet. That is 8. And then the middle nitrogen has 4 lines coming off of it, and each of those is 2, so that's an octet. And then this last oxygen has a bond and 3 sets of 2 dots, so that's also 8. So A, everything is an octet. So everything is an octet for the first one. Let's check the second one. This first nitrogen, yes. This middle nitrogen, 2, 4, 6, 8, yes. And that oxygen here, no. That oxygen only has 6, 2, 4, 6. It's missing. I'm going to erase these other 2 so we can see it. So that one does not have an octet. And let's check the third one. 2, 4, 6, 8, yes. Middle nitrogen, 2, 4, 6, 8, yes. And this third oxygen, there we go. That one has an octet. So B is eliminated just by checking octets. So now we need to go back and count total number of electrons. So I'm going to clean this up. And let's count electrons now. 2, this triple bond is 2, 4, 6. Oh, let me do it the way I did it previously. So 2, 4, 6, 8, 10, 12, 14, 16. Okay, so this one has 16. Has an octet and 16, so A is a contender. Let's check C. 2, 4, 6, 8, 10, 12, 14, 16, uh-oh, 18. Too many electrons. So the second one is A. Has an octet and exactly 16 electrons drawn, which we were able to determine by adding the electrons together from each nitrogen. Each brings 2, or sorry, there's 2 nitrogens, each bring 5, and the oxygen brings 6. So we're looking for 16 and octets. So here's the work, here's us checking, and then let me just clean this up and I can take one more shot of the correct structures for both. So there's the structure for A, and here is the structure for C for the first one. There we go. There are the 2 correct Lewis structures. Try these out. I'll pause for just a minute, but this is our last little bit of practice. Draw a complete structure. Finish the bond types, single, double, or triple. And same thing on the third. It's going to be single, double, or triple bond for the red question marks. And for the oxygen, how many non-bonding electrons do I need to attach? How many dots do I need to attach to the oxygen here to make sure it's stable? Checking our work. Number 1, to make sure both carbons have an octet, it should only be a single bond between them. For number 2, to make sure both carbons have an octet, right now each carbon only has access to 2 electrons. So if they share a triple bond, then both carbons should have an octet. Notice again, each hydrogen is only okay with 2. Hydrogen's always going to be on the outside. Hydrogen's always going to be terminal atoms. They're never going to be in the center taking all single, double, triple bonds. The carbons are the center atoms. So a single bond and a triple bond. So from these 2 diagrams, 1 and 2, you could probably guess what a double bond would look like, or rather, how many hydrogens would be needed if the carbons had a double bond. So if there's a double bond between carbons, what would the outside look like for if you're just adding hydrogens? So that's a side question that could be asked from this. And this last one, let's check to see if you got this right. Hopefully you're just sketching this out and trying it and just making a guess of what works, making sure you're checking octets. The main goal here is that everything has an octet. Don't worry about the total number of electrons with this activity, number 3. Just make sure everything has an octet. And the way I did this is I start with oxygen. Oxygen is on the outside, and so that one might be easier to do. For oxygen to have an octet, this one has to have a double bond. Just making sure oxygen has its octet. So now carbon has a total of 3 lines coming off of it. To make sure carbon has an octet, it's only going to be a single bond between that carbon and nitrogen, the second carbon and the nitrogen. So now we've narrowed it down to just the first carbon and the nitrogen, and this should be a double bond. And if we check, nitrogen has an octet, both carbons have octets if we draw it this way. And anytime oxygen has 2 lines coming off of it, that counts as 4 electrons. So there's 6, and there's our 8. So this oxygen should have 2 sets of lone pairs, or a total of 4 non-bonding electrons attached to it as well. This would be a complete Lewis structure where everything is an octet. That's it for today. These are our examples I wanted to go through, and you can review this to practice. Now the assignment 4 has you just drawing some structures from scratch. I have, on the previous lesson, walked through a couple of them. I have a snapshot of how I've started a few of the questions. Let me show you how to start some of the later ones. And I'm just going to arrange them in general order. So if you want to look at assignment 4 and look at how I've started some of the questions, you can do that. Let me show you what that looks like.